Lewis symbols and structures. Now here, very important topic in chemistry. Because finally we get to a nomenclature, a way to symbolize covalent bonds. And it kind of works for ionic, but mostly covalent bonds in a way that really simplifies things and lets us see what's truly happening with these electrons in these bonds. And I think the best way to do it is just to dive in here. So let's start off thinking about the simple case, the ionic, and then we'll move to covalent. Okay. So calcium. We'll go back to our example there. Calcium likes to be 2+. Now, remember we said calcium was bring up the periodic table here. Right there, calcium is a 4s2. So it had everything like an argon and then a 4s2. And we said before, if we make it calcium 2+, we're removing those 2 electrons. Okay, and so here it is, calcium. I'm drawing only the valence electrons here because it's a 4s2. The other ones, the inner electrons, remember they're not really involved with the bonding. They're hidden on the inside. They're the core electrons. Don't need to worry about theirs. I mean, they're there, but don't need to draw them. All right, they're not changing. There's nothing exciting happening with them. All right, and so we only draw the valence electrons, and since it's a 4s2, 2 electrons are what we draw, 2 dots. You could do it this way. You could spread them out. It really doesn't matter. Now, again, why 2 electrons? Because it's a 4s2, and notice, of course, calcium is in the second column, and so, second column, 2 electrons. If it was in the first column, I draw 1 dot for 1 electron. Right? If it's in carbon, that's the 4th of the main group, 1, 2, 3, 4. And so carbon, I draw 4 dots for its 4 valence electrons. All the way up to fluorine here with chlorine, bromine with its 7, or if I want to do the noble gases with their 8 electrons in the outer shell. Okay, and so here's a nice little chart summarizing that. These are, again, Lewis symbols and Lewis structures. So sodium is a 3s1, it's in that first column, so we put 1 dot around sodium. Right. Phosphorus, all right, it's in the 5th column over. It's got 2s electrons and 3 p's. 5, it's in the 5th column over, so there's this phosphorus with its 5 dots. Okay, fairly straightforward. Now, if we're going to make an ion, well, if we're making a positive one, we remove a dot or 2 or 3. Right? If we're making a negative one, we're adding a dot. Those dots are the electrons again. And so chlorine usually has 7 valence electrons. If I add an electron, now it's got 8. Now it's Cl- with its 8 valence electrons. Okay. And if you notice something, that if you think about the periodic table, if I thought I hit it. Oh, I hit the wrong thing. Let me go to this one. All right, if I'm looking at the periodic table, if I'm looking at those main groups, like magnesium, I've dropped 2, then I'll be like a noble gas, right? Or oxygen, if I gain 2, I'll be like a noble gas. Either way, those noble gases are 1, 2, 3, 4, 5, 6, 7, the 8th column over. And so it looks to me like 8 electrons in that outer valence shell will get you to be like a noble gas, whether you're gaining or losing them. Keep in mind that if I did this to the transitions or the inner transitions, those are in a energy shell slightly lower than that outer one. All right, so like, for example, here, this is the 4s, but then I drop down to the 3ds, and then back up to the 4p's. And so that outer one always has just the s and the p's, and so 8 electrons is always going to get you to be like a noble gas. All right, so that's called the octet rule. The idea, if I want to get like a noble gas, I want to look for 8 electrons in its valence shell. Right? I sometimes like to call this noble gas rule because there is a simple one exception to that, and that's helium. Helium only has the one shell, which only has an s orbital, and so helium can only hold 2 electrons, something that small. So it's not really an octet; it's 2 electrons. So hydrogen, if it gets 2 electrons, somehow it'll be like helium, the noble gas, and so it's kind of like the 2 electron rule for hydrogen. Or lithium, again, with its 3 electrons, if it loses 1, it'll be like helium, and again, noble gas like with its 2 electrons. But everything else, carbon, nitrogen, oxygen, they like to get up here like neon with 8 electrons, or these guys like to lose electrons to be like these. Those will all be 8. So for the most part, yeah, it's the octet rule, because neon, argon, krypton, all these do have 8 electrons in that valence shell, but helium is the one exception. It's just too small. It's only going to have 2 electrons. All right. Either way, we're trying to get to be like a noble gas, which is particularly stable. All right. So if if I've got sodium here, here's Lewis structure. It's in the first column, so it has 1 electron. There it is. Chlorine with its 7 electrons, there they are. If I transfer that 1 electron from the sodium to the chlorine, now I look like this. Sodium is positive, chlorine's negative, but this has a noble gas configuration, this has a noble gas configuration. See, they are both more stable. They're a lower energy in that as being ions in that configuration of a plus and a minus. And then, it's kind of like an afterthought, they say, oh, look at that, I'm positive, I'm negative, and so in electrostatics, opposite charges attract, and so they, boom, are drawn to each other, and you have sodium chloride, table salt. And so the whole point is to be like a noble gas, get to be that octet rule. Once you get the octet rule, because you have charges, they're going to stick together. And there you've got an ionic bond between a metal and a nonmetal. All right, covalent bonds are more easily understood, I think, and better serviced by these Lewis electron dot structures. And so, for example, chlorine gas. Chlorine gas is actually Cl2. So these diatomic gases. And you look again, if I tried to do an ionic bond with a chlorine, make it Cl2 somehow, ionic, 7 electrons and 7 electrons. If I transfer one over, hey, this one's got an octet now. Yay, it's like noble gas. But this one is further away. I mean, it used to have 7, now it only has 6. It's gotten worse. If I'm trying to get as close to or hopefully right on a noble gas configuration, Cl plus is the wrong direction, isn't it? And so I can't do it as an ionic bond. So instead we share. Here's the left chlorine with its 7, the right chlorine with its 7. Again, that potential curve, right? If I bring them close together, they start sharing those electrons. In particular, all it needs to do is share a pair. One pair of electrons, I've highlighted them in yellow here, being shared will make each one think it's got an octet, more or less think it. Oh, here purple, I'll use that. Look at this chlorine here. If it sees like those guys, see, it thinks it's got an octet because, well, 2 of them, they're being shared. For the right chlorine, same idea. If I circle those, it thinks it's got an octet. And so by sharing those 2 electrons, that pair of electrons, each one is actually more stable. Maybe not as stable as a true ionic bond where you'd give it 100%, but half the time being like a noble gas, the other half time not, they're still more stable, and so we get a lower energy, more stable configuration, which we call a covalent bond. Now, you could draw it like this, but much better when you have a shared pair of electrons, draw it as a line, because there's the bond. It's those 2 electrons being shared. And by the way, they're always in pairs too, because you always get kind of one from each one. It's always pairs of electrons we're talking about. Also, and with atomic orbitals, don't forget the spin up and the spin down. So again, you get this natural pairing of electrons. So we always think about it in terms of pairs. So there we go. That line right there is my covalent bond. That line right there is actually a shared pair of electrons. Now these ones out here that are not being shared, they're still being owned by this chlorine or over here. Those are called lone pairs. They're just out there all alone. They're not being shared. They're still 100% owned by their atom, right? So we have shared pairs of electrons and lone pairs of electrons. So kind of 2 classes, if you will, of them. Either way, they're like noble gases, and so they're pretty happy. Here's another example. Hydrogen, probably the simplest gas I can come up with, right? Hydrogen, 1 electron each, so I bring them together, they share that pair. Now they're both like helium because they each see those electrons that are being shared, so that one sees that one sees those 2. They both think they're helium now, and they're happier. All right, and so we're sharing that, and there's a covalent bond. Interestingly enough, we can share more than just a pair. We can share 2 pairs. We can share 3 pairs sometimes. And that works too. As long as we can get them up to be like a noble gas, they're happy. So H2CO, formaldehyde, good example of it. Here is what the Lewis electron dot structure looks like. And we'll talk about how to get to this next section. But if you look at this, if I'm looking at the hydrogen, yay, it sees those 2. It's like helium. It's happy. This hydrogen, same idea. This carbon is seeing all of those shared electrons. So if you count those up, the carbon sees 8. Hey, octet rule, it thinks it's like a noble gas. And this oxygen, if you circle the ones that are being shared there, it also sees 8. And so everybody thinks it's a noble gas. because we're sharing those electrons. And so everything's happier, everything's lower energy. And if I draw those shared electrons actually as bonds as lines, there you go. That's what that structure is best represented as. So there's formaldehyde. And you see I've got two lines here because I actually had two pairs of electrons that were being shared between the carbon and the oxygen. So if you only have a single bond, like up here, when we did this, that's called a single, if you only have a single pair that's being shared, that's called a single bond. If you're having two pairs, well, that's a double bond, and we represent that with two lines. I think that makes sense. Carbon monoxide actually has a triple bond in it. It's actually sharing three pairs. But again, if you look at what each one atom sees, thinks it's owning, or at least share owning, however you want to think about that, there are actually three pairs that are being shared, so that's a triple bond in carbon monoxide. Alright, so let's figure out, how do you actually come up with these Lewis structures? How do you get the right number of electrons? How do you figure out whether they're single or double or triple bonds and lone pairs and all that jazz? Alright, this series of steps here, 1 through 4, will lead you to the right structure all the time. They're not too hard to follow, but it does take some practice. All right, so let's go through this, and then I'll do several examples for you. All right, so how do you figure out a Lewis structure like the ones we're just talking about? Number one, count the total number of valence electrons. Just count them up. That's for every single atom that's going to be part of this molecule. Just get a grand total. Number two, arrange them more or less symmetrically, if at all possible, and connect everything with single bonds. All right. So a symmetric arrangement, nature does like to do symmetry when possible, and if there's any doubt whether which atom should be in the center and surrounded by the other ones, usually the center atom is the least electronegative, and so you can always look at the chart of electronegativity and put the least electronegative one in the middle. Usually there's not much of a confusion over which one should go in the center, but again, if there is, just do it that way. Number three, add lone pairs to give everybody an octet. That's what we're after, right? Noble gas ones, except for like hydrogen, it only gets 2 electrons, right? But octets for everybody. Just add those electrons on. And then number 4, count the number of electrons you've used. If it equals what you came up with in step 1 here, the total that you had available, then you're probably done. Looks good. Often though, you will not have the right number of electrons. If you use too many of them, well, we're going to remove some electrons, but we can maintain octets by giving double and triple bonds. I'll show you that. If you use too few of them, add the extra lone pairs of electrons to the central atom. Alright, that probably is very hard to understand if you just were given it. Many examples will help. Alright, so the first one here, silicon with 4 hydrogens. Let's go through those steps. Step 1, count the total number of valence electrons. So here we go. Silicon, if I go over to the periodic table, where is silicon? It is right below carbon, right there. And so it has, count them over, 1, 2, 3, 4. It's in the 4th column, so it has 4 valence electrons. 4, that's how many it's bringing in. All its other ones are inner, they're core electrons, they're not going to be used. Then I got 4 hydrogens. Hydrogen is in the 1st column, it's only got 1 electron that it brings in, right there, hydrogen, and so, but I got 4 of them, so there's 4 more. That's a grand total. 4 plus 4 is 8. 8 electrons to work with. Alright, arrange them symmetrically with single bonds connecting everything. That's step 2. Symmetric, so yeah, I mean, I could do it some weird way like H, Si, H, 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 but I mean, that's not symmetric at all. No, we're not going to do that. Do it nice and symmetrically like this, and put everything with single bonds. Okay. Then, step 3, count to see how many, well, actually step 3 is to give everything octets, right? Add lone pairs to give everything an octet. Well, let's see. Hydrogens, well, the octet for hydrogens is 2 electrons, right? Because it's the small one. So every hydrogen here sees 2 electrons. Again, the idea of the sharing, right? This one, there's 2 electrons in that covalent bond, so the hydrogen thinks it has 2. Same as for the other hydrogens. And then the silicon, right here, if I was to circle everything silicon sees, 2, 4, 6, 8. Remember, each bond is 2 electrons. And so silicon sees 8. It's pretty happy with that. And so, yeah, everything has octets. We're good. Go back up here now. Step 4. see how many you've used. If you've used too many, doubletrons. If you've used too few, add the lone pairs. So we got to see how many do we actually use when we made that molecule. So let's see, count how many of I got. 2, 4, 6, 8. I've used 8 electrons to actually make that. Hey, I had 8 electrons available to me, so it sounds pretty good. There we go. There's the Lewis electron dot structure for SiH4. Example, CHO2 minus. Okay, as usual, let's go through the steps. We've got a carbon with its 4 valence electrons. A hydrogen has 1. We've got 2 oxygens. That's in the 6th column over. So each one brings in 6. There's 2. That's 12. And then you got your minus charge. That's an extra electron. Can't forget that. Add that all up together. Looks like 18 electrons. So 18 electrons to work with here. Let's arrange it symmetrically. So I'm going to have my carbon, I'm going to have an oxygen, and a hydrogen. So there they all are. Give everything an octet. There, that oxygen now sees 8 electrons, right? 2, 4, 6, and 8. Don't forget those bonds have 2 electrons in them, right? This oxygen, there we go. It sees 8. The hydrogen's okay with its 2 electrons being shared, and that carbon only has 6, right? 2, 4, 6. So I gave it a lone pair. There's 8. All right, so everything has an octet. Looks good. Well, let's see how many electrons we used. Count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I used 20 electrons. Whoops, I only had 18. All right, so if I go back up here, again, this is what we're talking about with this number 4 rule. Hey, if you use too many electrons or if you use too few, this is the first case. I've used too many electrons. I got to make some double or triple bonds to fix it, right? I only have 18 electrons available, yet I took 20 to make that structure. All right, so here's the idea. If I look at an adjacent pair that both have lone pairs, like this carbon has that lone pair here, and the oxygen has a whole bunch of lone pairs. If I take away those lone pairs and move them into a double bond between them instead, right? So I'm going to take my eraser, and this one here, I'm going to go ahead and erase those. So I'm down by 2 electrons. This one I'm going to erase. So I took a pair off of each adjacent one and instead make a double bond between them. Okay. What does that do? Well, you see this oxygen still sees 8 because it's being shared, a double bond now. This carbon still sees 8, so everything is still obeying the octet rule, but by doing that I've dropped my electron count by 2. A pair is gone now. If you don't believe, let's go ahead and count. 2, 4, 6, 8, 10, 12, 14, 16, 18. Yay, so now I'm down to 18 electrons, which is how many I have available. So that looks pretty good now. Everything has an octet, and I've used the correct number of electrons. All right, so there's my structure. Now, one other thing about Lewis structures, this has a negative charge on this compound. Lewis structure, you have to indicate that it's a negative charge molecule, and we do that with big giant square brackets and put the charge on the outside. So there you go. There's my final structure for CHO2 minus. Let's try another one. NO plus. All right, so nitrogen has 5 electrons, oxygen has 6, and then I've got my +1 charge. That actually takes away an electron, right? That's how I get a positive charge, by removing an electron. So that's a grand total of 10 electrons now that I have to work with. 10 of them. All right, arrange them symmetrically. I don't know how else to do that. Pretty simple. Give everything an octet. There we go. Count how many electrons I used. 2, 4, 6, 8, 10, 12, 14. 14. Whoops, I'm up by 4. Well, I'm just going to do this twice now. Make a double bond and then make a triple bond, and that'll get me down to the correct number. So my eraser, here's a pair here on the nitrogen and a pair on the oxygen. So let's remove those and instead make a bond between it. See, so now I'm down to 12. Every time I do that, I drop by 2. I got to get down all the way to 10, so let's do it again. Whoops, eraser. Those are gone, those are gone, and make it a triple bond. So now I'm down to 10 electrons. Looks good. And so everything still has an octet. You can verify that. Oops, it's got a plus charge, so I put the whole thing with a plus there. There's my final Lewis electron dot structure for NO+. It's kind of like a little game. It's kind of fun to actually do this. Sit there and do it for a long time. And the more you do, by the way, the better you get, and you get pretty good at them after a while. OF2. All right, oxygen has 6, 2 fluorines. Each one of them has 7, so that's 14 grand total. 20 electrons to work with here. Okay, a symmetric arrangement. We put oxygen in the middle and fluorines on the outside. Give everything an octet. There we go. Everything sees 8 electrons now. How many did I use? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 I've used. Hey, I had 20 available. No charge on this one. There's my final answer then. There's the Lewis electron dot structure for it. Alright, so those steps will always get you. I know we still have to illustrate that one with what if I didn't use enough electrons, and we'll get to that real soon here. Okay. There are a few exceptions to the octet rule. Well, I've already talked about one actually with the hydrogen idea, because it's just too small. Get 2 electrons on hydrogen and we're happy, right? But there's a few other exceptions to the octet rule. All right. Number 1, again, hydrogen, helium, 2 electron rule is what it is. Number 2, if you have an odd number of electrons. So what if everything's not paired? You get 1 electron just kind of out there. Right? If that happens, that's called a free radical. You have this unpaired electron. They're generally very reactive, and they very quickly react with something else to form a more stable compound. Because free radicals are so reactive, they actually can be fairly damaging to the body and to the cells and the chemistry. And if you have free radicals in your body, they can do some damage, and it's good to get rid of them as soon as possible. And that's actually, like vitamin C is one of the things that it does. It's known as a free radical scavenger. It very quickly finds and eliminates these free radicals. All right? So an unpaired electron is a free radical. Right? Well, if I have an odd number of electrons, I'm not going to be able to get to an octet, which is an even number. And so you do the best you can. I mean, there are these molecules that don't fit our little human rules, I'm afraid. And so let's try one of those. NO, nitric oxide. All right, well, let's see. Nitrogen has 5, oxygen has 6. Yeah, look at that. Grand total of 11 electrons, an odd number. So I know I'm going to have a free radical right away. Let's do it. Nitrogen, oxygen, give everything an octet. Looks like that. How many electrons did I use? 2, 4, 6, 8, 10, 12, 14. 14. Well, let's see. That's too many, so I start knocking them down. I say, hey, let's take a pair off of here and a pair off of here and put it as a bond instead. That brings it down to 12. Now, if I did another pair and brought in a bond, that'd bring down to 10. So right now I've got 12. I could get down to 10, but the real answer has 11 right in the middle. So I can't do another bond, that kind of. All I can do is remove one more electron from somewhere. Where am I going to? Well, I can't remove the shared ones. They're pretty much locked in. I can remove one of these lone ones. And what I'm going to do is I'm going to go ahead and remove one from the nitrogen right there. And so let me just darken the other one so you can see it here. Make it very clear. These are the electrons that remain. I've got these pair, lone pair, lone pair, lone pair. Here's my free radical. There's that lone electron right up there. But if I look at this, I've used 2, 4, 6, 8, 10. I've used 11 electrons, which is correct. That's how many I have available, is 11. And, well, the oxygen has an octet anyway. The nitrogen only has 7. But again, this is one of these exceptions to the octet rule. It doesn't happen a lot, but every once in a while you might see it. By the way, why did I choose to remove it from the nitrogen rather than the oxygen? Well, the oxygen is more electronegative, which means it wants electrons more than the nitrogen does. I could have done it, I guess, from the oxygen, but that would have been a less stable arrangement. Leave the electrons with the most electronegative atom, right? Remove that one from the least electronegative, and that'll be your best answer for the Lewis electron dot structure. The third exception to the octet rule are called electron deficient molecules. This is where the atoms are just too small. They just don't have enough electrons to make it up to an octet, no matter what. Okay, they really only happens with 2 atoms, and that's 2 elements, I should say, boron and beryllium. And if you look at the periodic table, beryllium is over here, number 4, only has 4 electrons to its name, and boron over here, number 5. All right, beryllium has 2 valence electrons. It's in the second column. Boron, 3 valence electrons. Right? They just don't have enough to get to an octet. And so what are you going to do? All right? And they are an exception to the octet rule. Let's try this one. BF3, stable compound. If we try to do the Lewis electron dot structure, boron, again, it's in the third column over, so it's got 3 electrons. I got 3 fluorines, 7 each, so that's 21. Grand total, 24 electrons to play with. All right, arrange them symmetrically. fluorine, fluorine, fluorine. All right, and I've got 24 to work with. So if you think about this, I've already used 6. If I start giving everybody octets, like I give all these fluorines octets as normal, okay, then what have I got here? 2, 4, 6, 8, another 8, another 8. That's 24 electrons right there. I did not give boron an octet, and yet I've already made it to 24. All right. If I put that one in, bring it up to 26. Right? And so this one, BF3, actually looks correct with only 6 electrons for boron. Normally I would not do that. Normally I would say, hey, we can get down by doing double bonds, but boron is too small. You can't do that with boron. Right? So beryllium and boron, they're the only two you ever have to worry about, but keep it in the way back of your mind. If you're doing a compound has boron or beryllium, it may be an electron deficient molecule, and it's okay to leave those guys with less than an octet. Right? So again, it's an exception. You're not going to have to worry about it usually. The last type of exception are hypervalent. Hypervalent meaning they have more than 8. So if the electron deficient ones are the small guys, boron and beryllium, the hypervalent that have more than an octet, they must be the big guys. So big atoms can do this. They're big enough, they have enough energy levels, they have enough orbitals available where they can actually go beyond 8. They can go to 10, 12, 14 electrons sometimes surrounding them. Right? The general rule is if that central atom, that's the one that's almost always the hypervalent one, okay? If that central atom is at least a phosphorus or bigger. Look at the periodic table. A phosphorus is sitting right there. It's about halfway through the p block of the third energy level. That's the 3p. And if you think about that, the third energy level has S's, P's, and D's. Okay, but see, if I'm working over here phosphorus, I haven't made it to the D level. This is a 3p3. I'd have to go all the way to, let's see, 17, 18, 19, 20, 21 scanning before I start touching the 3Ds normally. And by that point, I've already added some 4s electrons. Right? So this phosphorus is sitting here. It's got, let's see, well, it's got neon, and then it goes over here, 3s2, 3p3. There's its electron configuration. And yet it's got these empty d orbitals, these empty 3d orbitals, 3d, yeah, which are not being used. That's extra space that could accommodate electrons, right? You could argue the same thing for aluminum, silicon. Just don't see that very often. Once in a while, I think I've seen it with silicon. I don't know if I've ever seen it with aluminum. Phosphorus is the first one that you typically see it on, and then anything really beyond that, they're all big enough where they could expand their octet. That's a kind of a strange phrase, an expanded octet, but you'll see that used. It just means we go more than 8. All right, so if you got phosphorus or bigger, be prepared for that to happen. So let's try this. Phosphorus with 5 chlorines, so PCl5. Phosphorus, again, it's in that 5th column over on the periodic table. Just show that again. 1, 2, 3, 4, 5. There we go. There's the column with phosphorus, so it has 5 valence electrons. And then I've got these 5 chlorines. Each one has 7, so that's 35 there. Grand total 40 electrons to work with. All right, so put phosphorus in the middle. Chlorine, 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 chlorine. Well, gee, with those 5 chlorines, I've already expanded my octet for that phosphorus, right? That phosphorus already sees 10 electrons. It's already violating the octet rule. Anyway, let's continue. Give everything an octet. So octets for all these chlorines go all the way around. Each one has these lone pairs that you need to add like that. All right. Phosphorus, well, it's already got 10. Like I said, I don't need to give it any extras there. How many electrons did I use? Well, let's see. This chlorine's got 8. So does this one. 8, 8, 8. That's a grand total of 40 electrons. And what do you know? That's what I had is 40. And so that looks pretty good. Again, the odd thing, that phosphorus has 10 electrons, but it's okay. It's big enough. It's allowed. That's the hypervalent. So these hypervalent, these expanded octets actually happen quite often. It's not unusual to have these larger atoms, and that's what they do, and it's okay.